Western civilization is moving closer to a point of irreconcilable, unstable equilibrium, as frighteningly increasing numbers of people trust nothing. Media, academia, and especially the governments are no longer held in high esteem. Regaining trust is often impossible after betrayal. However, transparency is essential to any healing process, and that is the essence of the Don Sullivan Show. Please listen to the team explore, probe, and debate cutting-edge science, technology, and computing. Play ball! Welcome back, everyone, to the Don Sullivan Show, the show where we discuss all things science, technology, and computing at a level that can be understood and absorbed by your average, smart American teenager. Today, we have another wonderful show for you, and thank you for the audience, the ever-increasing audience, I might add. Thank you for listening. Thank you for downloading. Thank you for making us as famous as we've now become. I'm your host, Don Sullivan, but I want to introduce to you my partner, Mr. Jersey Steve. Say hello, Steve.
Greetings from New Jersey. And before I pass it back, I just want to give a shout out to axedinc.com. You can support our wonderful producer by visiting axedinc.com. That's AXTINK.com. Subscribe to his YouTube channel and help support his efforts to create humorous animation as well as run our website, all while researching a cure for baldness.
That's just too good. And I am very thankful to all of our sponsors, present and future, hint, hint, hint. So we're going to get going here. And today I want to introduce you to our guest, as we always have on the Don Sullivan Show, another incredibly knowledgeable individual who we have worked with for a long time, Mr. Tony Foster. Tony, why don't you introduce yourself, and then we'll get right into a really interesting discussion about graphical processing units and the present state of supercomputing. Go ahead, Tony. Tell us about yourself.
Thank you for having me on, Don. I'm Tony Foster. I'm a senior principal engineering technologist at Dell. Guess that I'm getting a Dell guy.
That goes back a ways. Dating us, Tony?
It is dating us.
That guy had trouble, didn't he? I don't want to talk about that.
He did. It's okay now. He was on a commercial here about a year ago.
Was he really? Okay,
yeah.
That's great. I got to see that. Look that up.
Yes. So, yeah, that probably sounds really weird and far out as to what is an engineering technologist. I basically work with the engineers at Dell to take all the stuff that they find and figure out and turn that into something that a salesperson can use or a customer can use to make decisions about whether they need this in their enterprise environment. So that's really what I do.
All right. Well, we got a lot to discuss here, but I do, at the insistence of our lawyers, have to read our obligatory disclaimer waiver, and then we'll get right into this. So, once again, all statements by the hosts and the guests on the Don Sullivan Show are the personal opinions of the hosts and the guests, who all agree that the following content is the property of Zanalytics, LLC, to be used publicly and exclusively on the Don Sullivan Show. And if nobody disagrees, then we can continue. We're all good? Let's go. All right. So, Tony, let's start with this audience. Let's start by explaining on a very rudimentary level. I think everybody knows, for the most part, what a central processing unit means. Been around for almost a century now, to some extent, I think. But tell us what the real difference is between the present and the panacea of graphical processing units that you are such an expert on overall. Gina, we've had Gina Rosenthal on in recent episodes, and she just praises your capabilities to the high heavens. So tell us what a graphical processing unit is as compared to a central processing unit.
So let's put a little bit of history behind this.
Please do. I love history.
Yes, that way people have a little bit of context for what's going on here and why they're called graphical processing units and not something like AI processing units. So graphical processing units started all the way back in the very early 80s. Some people will argue back in the 50s, but we're going to start around the 80s. You needed some way to display the digital content that was coming out of computers on a screen. And so it's easy to argue that with the advent of the early computers, the IBM 8088, which is one of those big heavy boxes that has the big floppy drives in it, i.e. the save buttons, typically had two of those and had the giant black and green monochrome screens at a whopping between 12 and 14 inches.
Okay, Tony, the people under 40, they're not really, you're losing them already here. But yeah,
I know.
Yeah.
I remember the green screens and DOS and stuff like that.
Yes. Well, we needed some way to display all of those characters and stuff so you could play your favorite games.
Like Pac-Man?
Like Pac-Man,
there
yes.
You go, yeah.
Yeah, or Mrs. Pac-Man.
Mrs. Pac-Man, gotta be equal here. Gotta be
I don't have
inclusive,
to be equal,
yeah.
But I happen to enjoy Mrs. Pac-Man more than Pac-Man.
Oh, okay.
So,
well,
anyway,
Shocking revelations on this show today.
Being able to display that meant that we needed some sort of system to do that. And it wasn't a thing back in the day to build it onto the motherboards where the processing unit was, the CPU. They'd build it on as a card. So the first ones started out just displaying text and lines and certain things. And they kept growing and developing. And then in the 90s, they actually started doing 2D graphics rendering. And this is about the time where the term GPU came into effect, graphical processing unit. There were two big players in the market at that time, ATI and NVIDIA. ATI you probably haven't heard of because they got acquired. NVIDIA you probably have heard of because they're pretty big right now in the AI space. And later on, a few years down the road, they came out with a way to do 3D graphics rendering. And their CEO, Jensen Huang, actually defined what a GPU had to do. It had to be able to draw triangles and calculate shading and all sorts of other things. And this was the minimum benchmark for what a GPU was at the time. This happened around 97, if I remember correctly. And from there, it just kept snowballing and developing. And people figured out, hey, we can do complex math with this thing.
This is in the government, I think, if I remember correctly, that they first realized how incredibly fast these things innately were.
Yes. The government and NVIDIA both about the same time, depending on who you listen to, because I've heard both sets of stories.
So did they start out kind of geared towards gaming? Because isn't that really important
NVIDIA
for the gaming space?
And the point of it all was, but the government or some entities in the government realized that there could be alternative uses for this kind of unfathomable processing speed that, again, I guess is just much greater than the present or the contemporary CPUs at the time.
Yes. And the reason that they figured out that this was great is how a GPU actually does the processing versus how a CPU does the processing. CPUs typically run things in a linear fashion. So step one, then step two, step three.
Serialized.
Yes.
To a certain extent, yeah.
And GPUs can't process that way because when you think about graphics, you can't sit there and always go, first this triangle gets drawn, then this triangle gets drawn, then this sphere gets drawn. It has to be dynamic in how it draws things.
And almost
so,
in parallel,
very much so in parallel,
or at least concurrent operations happening.
It does.
Yeah.
Yes, definitely concurrent operations.
This is the best explanation I've ever heard of this, by the way. So listen up,
Awesome.
audience. Go ahead.
Awesome. And so because we could do these things concurrently with GPUs, the government and NVIDIA were like, we can do other things with this. We don't just have to calculate what a screen's going to look like when we're playing Doom, which is an old-time 3D game.
Well, that was one of my favorite games in middle school, Tony. I loved Doom.
Same here. So we don't have to do that. We can sit there and calculate ballistic missile trajectory. Yeah, I know, sort of morbid, but you can do it with the
I grew
GPU.
up in northern New Jersey. Everything was morbid on the streets.
Yes, or calculate the probability of multiple things happening, or the impacts of multiple probabilities happening to come to a central conclusion. So we can calculate all of those things with the GPU because, again, we don't have to do a sequential process. We can go and run things in parallel and see where they come out. And so that led to something called CUDA, which is what most AI platforms that use GPUs run on today. That's the language, basically how I'm coding it, how I'm programming it, and telling it what to do. That language really unlocked a lot of things. Primarily, it unlocked the predecessor to AI, which is machine learning and deep learning. And I don't know if we want to stop there or if we want to dig into machine learning and deep learning.
Well, this is a perfect segue here for the next question that I really had in mind for, and I was really wondering how we were going to segue this, but I really want to understand. I want the audience to understand, and I want you to be able to explain to this audience what a machine learning model is, and let's give us some examples of it, because this is really where the GPUs and some of these other advanced processors have sort of simultaneously allowed for this industry to explode really in a post-COVID world. And what I really mean is not just Silicon Valley or the computing industry, but AI. And so we talked, Tony, in previous, with Gina in particular, but also in previous episodes about how AI is kind of a buzzword to some extent, that it really is machine learning and what machine learning is to some extent. But please take this away and let's talk about machine learning and machine learning modeling now.
Awesome. So the idea behind machine learning is you can do all of these comparisons, these thought processes, if you will, in parallel. I can calculate the average of a bunch of different things.
And by a bunch, he means millions. So
typically millions. Now, you can have some smaller models that aren't millions, but typically millions at a time. And I got into a discussion with one of the professors I work with, because in my free time, I actually teach at K-State. I teach technology classes there. And
Kansas State, right?
Yes, Kansas State. Yeah, I know. Some people say K-State and mean Kentucky State, but no.
Kansas State. This is, if I remember, Wilt Chamberlain, I think, or is that Kansas?
That's the University of Kansas. KU.
Okay, I'm sorry.
They're rivals.
Oh,
boy.
Can't believe you
went there. Can't believe you went there, Don. Ah, man.
Sorry.
Anyway.
All right, I'll shut up. Let's get back to machine learning.
Okay. So we have these millions of parameters, and at this point, when you have millions of parameters that you're trying to calculate an average of, normally you'd sit there and calculate it out on a calculator or run it through a processor. Well, a lot of times that's ineffective. So that's where the GPU comes in. It can do a lot of this averaging of stuff and figuring out what is in the normal range. So something for people to go look up on their own, because I'm not going to get into a deep discussion on this, is standard deviation. If you go and find the standard deviation of things inputted into a system, you can figure out what's in the bounds of normal. And that means, let's say I have a picture of a cat. I can take that picture of a cat, break it up into little bits, and run it through these averaging sets. And let's say I have a bunch of averaging sets, and we're going to call those layers. So I have a stack of, let's say, 5,000 layers. I can take these chunks of this picture of a cat and pass it through there and let it run an averaging mechanism against these pictures of a cat. And when it comes down to the bottom layer, what we'll call the output layer, it can look at all of the averages that have come back from the machine and where they came back from and say, hey, standard deviation says this is a cat. I am 99% sure this is a cat because of how everything came through all of these layers of averages.
And this took a long time to do. This was, I think, called 20 years ago, we referred to this as the Google dog problem, where they really couldn't figure this out. And they couldn't until the processing power was sufficient through the GPUs, right?
Exactly. And it's also because of how the GPU is processing it. We can run all of these things parallel. We don't have to run them in a serial fashion. And that is a huge step forward. So now I know that this is a picture of a cat. I'm going to run a lot more pictures of cats through this model. And I'm going to make sure that it comes back and tells me that all of these pictures are cats. If it doesn't, then I need to go in and tweak some of the settings. I need to tweak some of them because the averages aren't averaging out to cat. Once I make those tweaks and everything, I'll try it again and see if it comes out. And this process of running all these pictures through and then averaging them out is training. And that's where we're training a model. And this requires a lot of GPUs or a lot of CPUs or a lot of something to do all of this work.
A lot of processors of different kinds, right?
Yes.
Possibly, yeah. Go ahead.
A lot of data too, I imagine.
It does require a lot of data. Like I said, we'll take like 10,000 pictures of a cat and drop them through and say, is this a cat? And we need a good majority of those pictures to come back as a cat.
So this is still, and again, Gina and I talked about this a few weeks ago. This is still mathematical arithmetic. This is really arithmetic interpolation and extrapolation taken to the infinite degree.
Yes. Yes.
Yeah. And it could still possibly get it wrong. But by getting it wrong, it gets better.
It does. It does get better. And by knowing that it's getting certain things wrong, because we can look at what's called a data set of pictures of cats that it didn't think were cats, we know where to go and change our layers and models and averages. We can make all of those adjustments to it and make it get better. So we can move that accuracy from, let's say, 80% accuracy on figuring out it's a cat to 90 to 95 to 98, 99% accuracy that pictures of a cat are a cat, all by sitting there just readjusting.
This is a human in the loop kind of process.
In the beginning, it was a human in the loop kind of process. As we grew these models and added more, I need to add some fine tuning on the ends or something, they started going through and adding some automation to it. Hey, this got thrown out. Why did this get thrown out? Let's tweak and restart the process. Just because when you're looking at millions of averages for a single layer, that's really hard for a human to control. It's not necessarily, I'm going to go tweak number 1542. I don't know that. I'm going to let a system help me figure out which one I actually need to tweak. So they started out when we were dealing with small models, tweaking them by hand. Now there's either assistance of another computer system, or it's fully automated, and as stuff's falling out, the computer system's doing it. And you might be going, well, how's another computer system know? And all I can say is, thank you everyone for going through those CAPTCHA things and identifying all the stoplights and buses and crosswalks.
I was thinking of that.
Because that is what's called tagging data. And so these computers that are helping us tune already know what the answer is, because we, the people on the internet, have already given it the answers.
So you're kind of grounding it against data that's...
Yeah, literally infinite amounts of data, but it could still be wrong. And if it is wrong, you have the end result, the final end point is going to be a human of some kind. At some point, it's going to be a human at the end that is going to say, this is just all wrong. And you kind of have to go back to the beginning and rerun the whole thing again to try to get it a little bit better, possibly. And
I think don't they pay people to do that? Isn't that
they pay us all on the internet. This is what happens, I think. Correct me if I'm wrong, Tony, but even with the standard Google searches right now that give you a explanation for the question as opposed to a list of links, that if you think it's wrong, you just ignore it completely. And that's, at least with Google, that's their feedback of saying, hey, okay, something's wrong with this. We need to go back and tag this one as not being quite right and rerun the whole thing again to get it a little bit better until the results within this reasonable set are accepted by the end users.
Absolutely. And that gets into another process altogether, because you don't necessarily have to rerun everything. That gets into RAG models, and I think we should save that one for another day.
We will, and we've actually mentioned it before, but now that you've tagged yourself, we are going to have you on in a later episode to talk just about those models themselves, because
RAG for RAG.
RAG for RAG, that's right.
Yes.
Let's look at a couple of other things, though. There are a lot of other interesting processors out there right now that aren't nearly as famous or as lucrative from a stock market perspective as GPUs, but they do other things. But they're also extremely powerful, and they're part of this whole thing. So the data processing units, which of course is a term from long ago, but has been rehashed in the sense that it's a new term, a DPU, and an IPU, which they both come from Intel and AMD. I think they both have them, the infrastructure processing units. And then there's super NICs as well. How do they all, or I just gave you three different things to explain, but how do they all fit into this model, which all leads to what the public sees as this sort of branded artificial intelligence, which is a term, of course, again, it's been sort of dusted off again from the 1950s and used in this marketing fashion.
Absolutely. So let's start with the DPUs. I'm a huge NVIDIA fan. I'm actually one of their enterprise advisors. And that's called NEPA for anybody who's interested in looking up.
Interested in another acronym that they don't have already? Yeah,
exactly. Okay. Yeah. But the idea there is you've got all these cards going back to what we started talking about earlier with the GPUs. We're not going to build the stuff directly onto the motherboard. We're going to put it on cards. And this is actually an interesting concept with the DPU. The concept is let's put some network interfaces on a card. And network interfaces are awesome. You might even be going, yeah, you can go out and buy network cards all over the place. They're cheap, whatever.
Best Buy.
Exactly. I can get them in USB, I can get them in whatever. What's new about this? Well, that's not what's new. What's new is what they added to the backside of these network interface cards. They're like, now let's put a processor, a CPU, if you will, on this card too. And you might be going, why a CPU? There's a CPU on the box already. There's one on the motherboard. We don't need another CPU, do we?
And for our loyal audience, we had a conversation with Oleg Ulyanov about some of this a few months ago as well.
Cool.
But in a much more a different fashion. But just
keep going.
Pulling everything together. Go ahead, Tony.
Awesome. Okay.
Yeah.
No, that's fine. And so we put the CPU on this card. Well, if we're going to have a CPU on this card, we're also going to need RAM, random access memory. That way we can store stuff in it. And you're like, wow, well, this is a pretty complex card to put in a box. Well, it gets even more complex because we're also going to add a GPU to this. So these are the 4 things that make up a DPU that are very, very interesting. The reason we need the processor is we need something that'll do serial processing. We'll run an operating system and stuff that's designed to be step 1, then step 2, step 3. So we've got to have that. Then we need something that can run all of these AI systems. And what those AI systems are vary depending on how you use the GPU or how you use the DPU. We also need some place to store all of that material to get everything going. And that's where the RAM comes in. We have this all on a card. We stick this in a server, and now we can do some really interesting things. For example, we can load an operating system on this card, not on the motherboard, not on the main computer that we're using, just on this card. And that means we can use the resources of the computer to do specialty tasks, to do stuff that we want it to do and don't want to steal resources with the operating system.
You can offload, which is
we
the
can
term
offload
you're going to get
it, yes.
to. Yep.
And so that's one of the nice things with the DPU. Now, where
it's really specialized in that sense, right?
It is specialized in that sense. What really makes the DPU shine, though, is we can start adding security layers and other functional layers to it. We can set it up so that it can see what's coming in and filter that according to what it needs to work on versus what it needs to send to the motherboard to work on. And with that filtering mechanism, you start making other things in the system more efficient. You can make your network communication more efficient because it can be intelligent enough to prioritize certain things over other things. So maybe we're running AI, and maybe it takes a stack of 8 computers to run this AI system. we can start to prioritize that. We can also add in security into that configuration to make sure that people aren't trying to inject bad information into our data stream flowing between the 8 systems. And that's just some of what a DPU can do. You can also use this to turn servers into other things. One of the favorite things that I've talked about
Sounds like
forever,
a transformer.
It very much so. One of the favorite things that I have been talking about since 2016 is offloading storage to GPUs.
Offloading storage to GPUs, not DPUs.
Not
to GPUs.
DPUs. And this was before DPUs existed. So 2016, I was saying, let's run storage with GPUs. Let's let GPUs control the storage. Well, remember I said the DPU has a GPU on it?
We're getting really circular logic here, but okay.
Yes. Well, there are many vendors out there now who have software modules that get loaded on the DPU and can turn a server into a storage system and can control all of the storage on that box and send it out across the network to other machines, turning it into what's called a SAN, storage area network.
So you really have everything on these DPUs that you possibly would want to effectively run an entire supercomputer.
Yes, absolutely.
I didn't even realize it went that far, but I got to ask you then how, and it's a bit of a different subject, but tell me about an IPU then, its infrastructure processing unit. That would seem to me, at least in terms of the name, to be a step beyond the DPU.
You can say it's a step beyond the DPU. So an IPU, this is another cool feature. And these are Intel and AMD based competitors.
Intel still
to the
got
DPU.
Something. We're
Yes,
happy
they
with
do.
that. Yes, they do.
Oh, I'm very happy with that. I'm very happy that they still have these. And an IPU takes that whole networking layer that we talked about up another notch. It makes it better at communicating across the internet. It makes it better at communicating with other devices. And it can bring multiple systems together as a single group of systems that are managed as one.
And the infrastructure name would imply to me that it does include multiple systems with some type of, I don't want to say virtual, but some kind of network or connectivity in between those multiple systems, effectively almost including a super NIC.
Yes. Well, thank you for getting that third item.
That's my job.
I was waiting on that third item.
That's my job there.
Yes, we have the DPUs, which are fantastic at what they do and really sit at just a single host or a single server or computer. Then you have the IPU that sits at multiple hosts and brings them all together. Now, Super NIC actually combines the state of the two DPU and the IPU, brings them together. And it has really, really, really fast NICs in them. Most home computers currently run about 1 gigabit per second, maybe 2.5 gigabits per second. Or if you're like me and have a bunch of servers tucked away around the corner, maybe 10 gigabits a second.
Yeah, we were talking a little bit.
We're talking a little bit faster.
Yeah.
In the range of 400 gigabits per second to 800 gigabits per second.
Yeah, this is getting into the speed of light here, and
This
Play Doom really fast,
yes, or whatever game of choice is. Yes, you can
So
play
these are the next. These Super NICs, IPUs, DPUs. These are the next kind of wave. This is the future.
Yes,
but it's now. The future is now in this case. They exist now, and as we get into
you don't hear
later
as much
questions-
about them though.
No,
and there's a reason you don't hear as much about them. And the idea behind this is we don't want to hear a whole lot about these because these are the things that make the connections and everything possible. Because as Don said, we're approaching that whole speed of light thing with Super NICs. And that's important because when we have these really, really big models like DeepSeek or, why my brain just completely failed on me. But any of the big models you can go out and type into on the internet and say, create a picture of, and you have these models out there, you've got to have really fast connections because we're talking about hundreds of computers all interconnected together running these models to figure things out.
well, I'm glad you mentioned DeepSeek there, Tony, because I really wanted to actually take the discussion of these physical components and bring it back to modeling and bring it back to the notion that the models, and this is the DeepSeek question as it stands right now. Obviously, it's got a lot of momentum in the press right now. These models are all built and made better, built on top of every other model that exists out there. So this is really a self-perpetuating super system that we are right now on the cusp of.
Yes, absolutely.
That's what DeepSeek did to a large extent to supposedly get greater results than some of what OpenAI had and so on. There's other things around that. I don't mean to oversimplify it, but that's part of what happened, right?
That is a good explanation of it. In my personal opinion, looking at all the information and stuff that is available, and there's not tons available, but what it looks like to me is they basically went on a mining expedition of the other models that are out there and used that to train their model.
And that's what David Sachs, the White House AI director, I suppose is his title, he kind of explained it that way in the weeks after that first announcement. David Sachs has not been on the Don Sullivan Show, but if you're listening, you're invited to come on anytime you would like, and we will have a special show for you. So continue, Tony.
It's awesome. And yes, it's good. And if you do something like that, and your goal is to be as good or just a tiny little bit better than a previous generation of model, really you don't have to train the model with all the data. You can just go mine the data off the other models, bring it into your model. There are ways to do that are way beyond the scope of this discussion. And then do a tiny little bit of tweaking and improvement on the model. And you can go, we've improved the model. We've got a better, faster model, and it took less time to train it.
Why? It wasn't built from scratch.
Exactly.
They skipped a lot of steps.
Absolutely. It was a bunch of step skipping. And so, of course, they didn't require all of these GPUs and all of these data centers to come up with this new model. We just went and basically found it on the public side of these models that are already out there for you.
It's sort of like if you were building virtual baseball players in a baseball player video game, and you were taking all of the best attributes from all of the best players in history and putting them all together so that you had Nolan Ryan's arm and Babe Ruth's left-handed swing, along with Ozzie Smith's range at shortstop, all together.
You would be accused of
Absolutely.
cheating in this scenario.
Well, I'm not saying they're using steroids. I'm saying
Or it's
they're using
unfair.
DPUs, IPUs, and super nicks. All right.
Yeah.
Hey, Tony, by the way, I have to have a baseball analogy in every episode. It's kind of a thing. So
Part of his contract.
Yeah, I completely understand. It's important that you get those things in there. Don't want to be in violation of a contract.
Yeah, I'm already embarrassed about Wilt Chamberlain, so I want to make everybody remember I have a different sport. I do know what I'm talking about with this stuff. Hey, I want to let's have two more questions for you, Tony. And as we've had such a rich discussion here, I want to kind of put them together into one and really ask you to prognosticate a little bit, to speculate into the future, because this is a lot of fun. And what's really going to be fun is I'm going to have you back on in 6 months from now and see how this prediction actually is turning out. As we've discussed all of these amazing components, which really didn't even exist in our lexicon before COVID, shall we say, whether it's DPUs and IPUs and Super NICs, starting with the amazing GPUs and the success of these companies, everything from the hardware, meaning NVIDIA, and to wherever OpenAI is going to go, public company or not. Where do you see this going in, say, 3 years? So I can hold you to this.
Awesome. I love being held to things that I have no control over.
That's right.
This will be great. So 3 years from now, I suspect that we're still going to see awesome things coming out of NVIDIA with new GPUs, new DPUs, new Super NICs, probably other new stuff that hasn't been in our lexicon before, where we're just going to keep getting faster and faster. I also think we're going to start.
We got that speed of light problem, though, is still there. So.
We do. But that gets me to my next part of this prediction. I think the next part of it that you're going to start seeing, and Microsoft announced here about a month ago, I think it was, a new form of a quantum computer.
Oh, there is a subject. And you have just tagged yourself, Mr. Foster. There you have just tagged us. There's a whole new subject, but go ahead. Let's tease it.
Yes. Let's put quantum computing on the shelf for another episode. But I think you will see quantum computing be this massive thing that's going to start really gaining legs in about 3 years or so, depending on what advancements we get in the field. So, like I said, Microsoft just came out with a new quantum processor. That means
Microsoft did. That's their processor. They're in the processing business now. Holy cow.
I think it was actually a company that gets funded by Microsoft. But anyway,
I'm being silly.
Let's not split hairs.
Control-Alt-Delete on
And I think that we will see many other competitors come out with supercomputers / quantum computers in similar fashion to what Microsoft basically announced. And I think that's going to start spurring innovation. And so in 3 to 5 years, you're going to see true quantum computers start to come to life.
Well, on that, Tony, that's an unbelievably cool subject. I assure you, audience, that we are not going to have classes on differential equations or the Schrodinger equation. We will exclusively have at some point in the near future, and Tony will be back on to discuss quantum computing, because it truly is the coolest subject that I have ever experienced or read about or just even seen in my 40 plus years in the computing industry. So with that, I think we're going to have to end this particular episode. It's been incredibly rich. I thank you so much, Tony, for joining us and becoming part of the Don Sullivan Show family. And we'll have you back on. Anything else you want to add to before we end this particular episode?
Of course, I'm looking forward to it. If people want to find out more about the crazy stuff that comes out of my head, they can go read my blog, which I sometimes post to, wondernerd.net. And yeah, it's been great being here. Thank you so much for having me.
We're going to have you back, Tony. And Jersey Steve, how about you? Anything else to add in here before we end this particular episode?
I'm sorry about the Wilt Chamberlain reference. I try and keep on top of Don.
Sorry, K-State people. I really blew that one bad. I feel
thank you for
embarrassed.
joining us, Tony. And that's wondernerd.net, correct?
Correct.
Awesome.
All right, everyone. Thank you so much for listening again. Please remember to tune in and download every episode of The Don Sullivan Show. And remember, folks, all at-bats are situational.